Welcome to this tutorial on how to analyze governance potential using a simple Python program. Have you ever wondered how we can evaluate different factors like demographics, geography, social economics, and behavioral patterns to determine a region's leadership potential? Today, we'll walk through a Python program that does that exactly. Let's dive in.
Before we jump into the code, let's break down the problem we are solving. We have 5 key factors. First is the demographics, the population characteristic of the region. Second is geography, the physical and environmental factors. Third is the socioeconomics, the economic and social conditions affecting people. Fourth is behavioral, the behavior and trends of the population. Fifth is governor value, the leadership influence in a region. By combining these factors, our program determines the potential number of governors needed for a given area. Instead of making random guesses, we use a mathematical formula to analyze these values and compute a meaningful result.
Now let's break down the code step by step. Python provides built-in math module that contains mathematical functions. In this program, we use math.ceil to round up our computed number of governors to the nearest whole number. Since we can have a fraction of a governor, this ensures that the result is always a whole number. Step 2. Creating the function. This function, complete regions, is designed to calculate the number of potential governors for a given region. It takes 5 parameters, which are demographics, geography, socioeconomics, behavioral, and governor value. These inputs represents different factors that influence governance decisions. The function then processes these inputs to determine how many governors are needed. Step 3. Validating inputs. Before performing any calculations, the program ensures that the input values are within acceptable ranges. D, G, S, and B must be between 0 and 100 to ensure valid percentage-like values, while V must be non-negative because a negative governor the negative governor value doesn't make logical sense. If any input is out of range, the program raises a value error, preventing invalid calculations. Step 4. Calculating the potential number of governors. The program calculates the average percentage of a governance-related factors. Since D plus G plus S plus B gives a total score of 400, dividing by 400 normalizes it to a value between 0 and 1. This normalized value is then multiplied by V, which is the governor value, estimating how many governors are needed based on the given conditions. Step 5. Rounding up the results. Since a region cannot have a fraction of a governor, we use math.ceil to round up the result to the nearest whole number. This ensures that if the completed number is 3.2, for example, the program returns 4 governors instead. And lastly, step 6. Implementing user input in the main program. This is a special condition in Python that ensures the following code only runs when the script is executed directly, not when imported as a module in another program. Inside the block, the program does. The first one is prompts the user for input values. The program asks for values for D, G, S, B, and V, and then it converts them to a float to allow decimal values. The second one is calls the compute region function and display the result. It passes the user inputs to compute regions. It then prints the computed number of governors. And lastly, allows the user to repeat the process of exit. The user is asked whether they want to compute again. If they type anything other than yes, the program exits. And that's it for the code breakdown. Thank you.
So in this test run, we will analyze 5 different scenarios Using our divide and conquer algorithm for governance, we will compute the number of potential governors based on the different demographic, geographic, socioeconomic, and the behavioral factors. So the formula that we're using here is this. So the potential governor is equals to D plus G plus S plus B over 400 and times B. So where the 400 came from? The 400 is the maximum possible sum of 4 factors like 4 factors D, G, S, and B, each ranging from 0 to 100. So this ensures a normalized value between 0 and 1, making the computation fair and scalable before multiplying by B to determine the final number of regions. So let's try a test cases, 5 sample test cases. Let's run this program. So in the test case 1, let's start with 100, 75, 50, 40, and 10. So the sum of factor is 100, 75, 50, and 40 is equals to 265 over 400. We will get 0.6625, and multiplying it into this governor value, which is 10, and we get 6.625, which is rounded up to the potential governor 7. So let's try another. In this case number 2. Let's enter 71, 59, 99, 33, and 18. So the sum of factor of 71 plus 59 plus 99 and 33 is equals to 262, and let's divide it to 400 is equals to 0.655, and multiply it to the governor value, which is the 18, and we will get 11.79, which is rounded up to 12. So the potential governor here is 12. Let's try another cases. In the third case, we will try enter demographic 68, and in the geography is 56, 82 in socioeconomics, and behavioral is 62, and the governor value is 13. So in here, using the formula, this so the sum of factor of 68 plus 56 plus 82 plus 62 is equals to 268, and divide it to 400 equals to 0.65, and times it to the governor value, which is 13. We get 8.71, and we will round it up it to 9. So the potential governor here is 9. In the fourth case, let's compute again. In the fourth case, let's try the demographic 94, and the geography 75, socioeconomics 99, and the behavioral is 90. And the governor value is 8. So here, the same with these three cases that we test. The sum of factor is the 94 plus 75 plus 99 plus 90 is equals to 358. Divided to 400 is equals to 0.895. Then multiply it to the governor value of 8. And then we get 7.16, which is rounded up 8. So the potential governor of this case is 8. And let's try last or fifth case, the last test case. So in this case is the we will compute the low socio-economic impact. The demographic is 93. The geography is 56. Next 29. 60. Then the governor. Oh, there's an error. Let's try it again. Let's enter 93. 56. 29. 60. Then 4. So here, the sum of factor is 93 plus 56 plus 29 plus 60 is equals to 238, and let's divide it to 400 is equals to 0.595 multiplying it by V, which is the governor value 4, and we get 2.38, which is rounded up to 3. So the potential governor here is 3. In the first test case, we compute the high demographic and geography. 1. And the second case, we compute the strong socioeconomic. And in the third case, the evenly distributed factors. And the fourth case is the high socio-economics and behavioral influence. And in the last case here, we compute the low socio-economic impact. So in this test run, we analyze different cases where demography, geography, socioeconomics, and behavioral factors influence the number of potential governors. By applying the divide and conquer algorithm, we achieve efficient and strategic governance planning. The result shows that higher socioeconomics and demographic values significantly increase the required number of governors.
And that's how our program works. We took real-world factors, applied simple mathematical model, and used Python to calculate governance potential. This concept can be expanded further by integrating real datasets or adding more complexity to the calculation model. If you found this tutorial helpful, make sure to like and subscribe for more coding tutorials. See you in the next video.